Hello first year ECE students. So this video is on the left out portion of the third unit. As I said, so that portion is AC transients and Laplace transform method for the solution of transient response. These two topics are left over. So now I am covering these two topics by this video lecture. Okay. We have seen so far DC transients, that means transient response of DC circuits. DC circuits in the sense circuits excited by DC supply. We have seen how transient response can be determined, and we also solved some problems on that. Now the circuits, same circuits RL, RC and RLC circuits excited by AC sinusoidal supply. You see here, as I mentioned here, the procedure, you see here, the procedure for obtaining the transient and steady state response for AC excitation is similar to that of procedure explained in the previous section. Previous section means DC section. So the procedure is same. In that, in particular, the transient part, we know that the procedure contains determination of transient response and steady state response, the complete solution. The transient part is anyhow independent of the type of excitation. That is the reason why this is also called source free response. So it is independent of excitation, whether it is DC or AC, independent. So there is no difference in transient part calculation. In fact, there is no need to once again calculate the transient part of the solution. Only steady state part of the solution is to be determined. That also mathematically slightly different. So in that way the procedure is same for whether it is AC or DC. Now we will see the RL circuit excited by AC sinusoidal supply. You consider an RL series circuit. Here switch is there. The switch is closed to connect this supply, sinusoidal supply, at the instant t equal to 0. Now as before, here the supply is, before it's constant only V. Now you see here the supply is AC supply, that is Vm sin omega t. AC supply can be written like this, a sinusoidal function. Application of KVL, as it is series circuit, application of KVL results in this circuit, this equation. Previously here it is only V, but here Vm sin omega t. That is only the difference. Now initial conditions also mentioned here. We assumed that inductor has 0 initial current. You see, at t equal to 0 minus I is 0. Therefore at t equal to 0 plus also current is 0. That is mentioned here. It is not clearly visible. Here it is I of 0 plus equal to 0. That is written here. What it means, at t equal to 0 minus I is 0. Therefore at t equal to 0 plus also current is 0. That is about the initial. Now as before, by writing d by dt equal to d, the equation takes this form: d plus r by l I equal to Vm sin omega t by L. Previously here it is only V by L. Now it is Vm sin omega t by L. That is the difference. Now to determine the transient response, we consider no source. That means we solve only homogeneous part of this equation. That is nothing but d plus r by L I equal to 0. This is same as before. It has only single roots, minus r by L. If it is having single root, then the form of the solution will be like this: a e power mt or a e power that root equal to minus r by L. So the a e power minus r by L t. So this is the transient response, transient part of the solution, same as DC term. Now steady state response, this is slightly different. There in DC circuits, for determination of steady state response, we have written I from this equation, from this equation, I equal to what? I equal to Vm sin omega t by L, and this d plus R by L will go to this. So I equal to Vm sin omega t by L into d plus R by L. This is. Previously for DC circuit there will be no Vm sin omega t, but only V, that's all, constant only. Now this is the steady state for I from that differential equation. Now to determine the steady state response here, we have to substitute d square equal to minus omega square. In the previous case we substituted d equal to 0 for DC response. Here d square equal to minus omega square. To substitute this value here, just we rationalized the equation by multiplying numerator and denominator by R by L minus d, that's all. With that d square, we will get the term d square term, and in that d square term we will substitute minus omega square. After substituting and simplifying, we will get this equation. This is the equation. I equation is this. This is the steady state response. Steady state solution will be like this. In the previous case, whether you remembered or not, the steady state response for RL circuit is simply V by R, that's all. Here we get all these things. Okay. Now this can be written like this. Here to write this, okay, one step is missing here. Here to write this, here this denominator term R square plus omega square L square is written like this, root of, how it can be written, root of R square plus omega square L square into again root of R square plus omega square L square. Okay, wait a minute. Root of R square plus omega square L square into root of R square plus omega square L square into two roots. Now we know Z impedance, Z equal to R plus J X or XL. So impedance consists of real part and imaginary part. This is impedance value, this is real part and imaginary part. This can be represented by one triangle like this. These three terms, this is R, this is X, and this will be the angle theta angle, and this is equal to Z value, the magnitude of Z. What is the magnitude of Z? Equal to R square plus XL square the root. This is that value. So the impedance terms, we know real part is resistance, imaginary part is reactance, and the angle between that, the impedance angle theta equal to this R by, okay, theta equal to this, the angle between here. These components in the form of triangle we can represent. This is known as impedance triangle. From this hypotenuse is equal to impedance magnitude R square plus XL square. So root of R square plus XL means omega square L square. This is nothing but Z. Here one more root term is there. If you take that root term into this parenthesis brackets, now we will be getting what? I will write down here. You see this equation. How it can be written? V by root of the term into R, sine term is there, plus what is other part? Minus omega L cos term. Okay, minus omega L cos term. Here one more root is to be taken here like this, root of, and here also omega L by root of what? R square plus omega square L square. Here also same thing. Now from the previous one, impedance triangle, this is R, this is XL, and this is Z, and this is impedance angle theta. Impedance angle theta. Now this term R by root of R square plus omega L square. Root of R square plus omega L square means this Z. So R by this Z, how it can be written? This R by Z, how it can be written? This is nothing but cos theta. Cos theta equal to R by this magnitude Z. Z equal to root of R square plus. So for this we can replace R. Similarly for this, XL equal to omega L. What we can replace? Sin theta. Sin theta equal to XL by this. Opposite side by hypotenuse. Like that we get. So this is equal to sin theta. This is equal to cos theta from impedance triangle, where theta is impedance angle, R is the resistance real part, and XL is the. For RC circuit, in place of XL, we will get XC. XC, that you have to remember. XC means what? 1 by omega C. We will get XC, that's all. There also same thing. Z means difference is that. That you have to remember. So this R by root of R square plus omega square cos theta, and this omega L by this root term equal to sin theta. Then it will become cos theta sin omega t minus sin theta cos omega t. That is nothing but sin of omega t minus theta. Like that we have written. And here root of R square plus omega square L square is written like this. This can also be written as Z. Here it is not written, but can also be written as Z. If it is written as Z, then it is equal to Vm by Z sin omega t minus theta. So like that we can be simplified. This is simplified like this. That is important to understand. Same thing by using impedance triangle we have written there. This is given in RC circuit also. There also it will get the same thing. Okay. Now this is the steady state response. Okay. The total solution is what? Transient response plus steady state response, IT plus IS, written here. IS is this. over. Now we have to determine the arbitrary constants A, that's all. To determine arbitrary constants, we have to make use of initial conditions. Initial conditions are already mentioned here. It is RL circuit. It is RL circuit. So for RL circuit, before 0, before t equal to 0, the t equal to 0 means I equal to 0. Therefore, after t equal to 0 plus also current is 0. That is at t equal to 0 plus current is 0. We make use of that condition here at t equal to 0, that is t equal to 0. Here also t equal to 0. What is current? Current is 0. That we will substitute. 0. Here t equal to 0 means this is 0, it will become only A. A. Here also sine of minus theta equal to minus sine theta. From this A value equal to this, from this equation. So like that A value is determined. Now the complete solution is this. Just A value is written. See here. Now next, this is simplification. This is taken out. E power minus. So this is the complete solution of the RL circuit excited by AC sinusoidal supply. Okay. Here this is transient part. It dies or it reduces to 0 within a very short time, and after that this response will be final response, steady state response. Previously for DC circuit, the steady state response will be only V by R. Why? Because for DC, inductor act as short circuit, there will be no inductor, and the circuit consists of only R. Therefore, V by R, that's all. But here, this is not DC, so inductor will not act as short circuit. Inductor will function. So inductor will be there in the circuit. So as inductor is there, the circuit, the response will be like inductor term. You see, inductor term is coming into the picture. That means Z. If inductor and resistance are there, the circuit impedance is R plus J XL or R plus J omega L. Its magnitude value is this, root of R square plus omega square L square. So final response will be Vm by that magnitude Z sine of omega t minus theta. So this is the response. Like that, we have to determine the steady state response. Same thing for RC circuit. In place of RC, V. So we have written the KVL equation IR plus, as it is C, 1 by C integral I dt. To get the differential form, we are integrating this. Previously also we integrated this. But in the DC circuits, after integration, that means after differentiation, here we will get 0. Why? Because there we are having only V constant. If you differentiate, we will get 0. But here we are not having constant. Now we are having Vm sin omega t. So no 0. We are getting this value. So RHS value is something. We are having something. Previously, as we are having 0 here, the response for RC circuit will be only transient response only. No steady state response. You remember or not? For RC circuit excited by DC supply, the complete solution consists of only transient response. I equal to IT only. Why? Because here we are getting 0, that means homogeneous equation, no steady state. But here for AC circuits, no 0. It is non-homogeneous equation. We have both transient response and steady state response. But transient response is same. For transient response, we solve only this equation, d plus 1 by RC equal to 0. From that, we will get root, one single root minus 1 by RC, and the form of the response is like this. Steady state response same as it is before. We will write down the I expression, I value from this. From this, we write down the I. This is that I. And we will substitute d square equal to minus omega square. If the response is sinusoidal or cosine function, the steady state response can be determined by substituting d square equal to minus omega square. This is one method. Another methods are also there for obtaining steady state. This is one method that we are following. Next, one more thing. Here we considered V equal to Vm sin omega t plus phi. We can consider as Vm sin omega t only or Vm sin omega t plus phi. For RL circuit, we have taken the supply as only Vm sin omega t, not plus phi term is there. Plus phi term is also can be included, there is no difference. If plus phi term is there, we will be getting that extra, that's all. That indicates some initial angle at switch closing. At the instant of switch closing, we are at this angular. That is the indication that for the time being you can forget about it. You can treat it or you can consider it or not. Here it is considered, and at some portion it is not considered like this. If it is having, we will be getting at all places sin omega t plus phi, cos omega t plus phi, like that. So don't confuse that. It is, you consider it as only Vm sin omega t, or if you want to consider it as Vm sin omega t plus phi, here you treat that this phi is there. Okay, so this is the equation, KVL equation. We differentiated it. If you differentiate, this will be the form. Next, for transient response, we solve only this auxiliary equation. It has only one root. This is root. If it is having only one root, then transient response will be of this type. This is the transient response. And next, it has steady state response also. To determine the steady state response, what we did, we expressed I from this equation, I. This is that equation I. And in that we substitute d square equal to minus omega square. After substituting and simplifying, clearly given here, it is simplification. Just taking common like this. You see here it is clearly given. Previously, as I explained, you know, no? Z root of r square and taking one root term inside to this, and from impedance triangle, all these things I explained. Here you can notice that. You see this term r square plus root of r square plus 1 by omega square c square, that is r square plus xc square. It is RC circuit, so impedance equal to r square plus xc square. So that is written like this, root of this, and one more root term is taken inside. If you take inside, it will be here and here also. Same impedance triangle this is. Previously I said there, in place of omega L, we will be getting 1 by omega C. You see here, you see, angle. Now what it can be written? 1 by omega C. This term 1 by omega C by root of r square plus omega square. That is 1 by omega C by this one. That is opposite side by hypotenuse. What it is? That is nothing but sine of theta. So this is equal to sine theta. Similarly, this is equal to cos theta. This is, it is written here. Okay, impedance triangle and simplification. In the previous, in place of 1 by omega square, 1 by omega square c square plus 2, we will be getting only omega square L square here. If we represent that, this is the equation. Now this thing can be written as how it can be written as sine of omega t plus theta. Here also, as I just now said, if we consider omega t plus phi, you treat that is present here. If you don't consider, it is only sine of omega t plus theta, that's all. See. This term can be written as z as before, or you can write like this one. This is equal to z. What it is? This is the term. This is nothing but magnitude of z. If you write z, then here Vm by z sine of omega t plus theta. If we can observe RL circuit and RC circuit, for RC circuit we are getting sine omega t plus theta here, whereas for RL circuit steady state response, You see here, RL circuit, what we got? Sin omega t minus theta. Steady state response minus theta. What is this? For RC circuit, steady state response is what? Plus theta. If it is not there, omega t plus theta. So that is the indication. Here it is the expression for I. In I expression we are getting plus theta for RC circuit minus theta for RL circuit. It indicates that I leads the voltage that I said in the classroom. For RC circuit, current leads the supply voltage, whereas for RL circuit, current lags the supply voltage. Plus theta means leads, minus theta means lags. By what angle? Theta. Theta is impedance angle. That is, if V is some value, then current will lead by impedance angle theta in RC circuit, and in RL circuit current lags by the same angle. That you have to understand. So the complete solution will be now transient response plus steady state response. Now initial condition slightly varies here. It varies. Whereas in RL circuit I equal to 0. Therefore we substitute I equal to 0 there. But here the response, now we are having RC circuit, RC circuit excited by AC supply. Okay, at t equal to 0 minus, at t equal to 0 minus, Vc equal to 0, that is capacitor voltage equal to 0, that is initial value. So therefore at t equal to 0 plus also, Vc equal to 0. So immediately after closing switch at t equal to 0 plus, the circuit will now becomes how? Vc equal to 0 means short. Here it is short. So we have to replace it by short circuit. Short circuit means like this. Okay. This is V. V means Vm sin omega t. Vm sin omega t. And this is R. So what is the current? At t equal to 0 plus, as capacitor is shorted, we represent it by short. Now what is the current? I is nothing but this V by R. So Vm sin omega t by R. That is the current. Whereas previously here inductor. Inductor means before current is 0. So after immediately also current 0. Current 0 means how we can represent? How we will represent inductor? We will represent inductor by open circuit like this. Open circuit means current is 0. Now it is not inductor, capacitor. Capacitor is short circuited at t equal to 0 plus. So therefore we represent it by short circuit. Short circuit means current is there. What is that current? I equal to V by R. So Vm sin omega t by R. So that is the current. You see here. Vm sin theta or sin omega t by R. So that is the case. If we replace it by, you consider sin omega t plus phi. You consider that sin omega t plus phi is there. That is imply omega t plus phi is there. So at t equal to 0, this will become 0 and only sin omega t phi will be there. Vm sin omega, Vm sin phi. So here all these places phi is there. Here phi is there. Here also phi is there. Now what happens at t equal to 0? That sum 0, only sin theta. Okay. This is equal to, supply is what? Vm sin omega t plus phi. So at t equal to 0 plus means this is 0. So Vm sin phi, Vm sin phi by R, that is the current. So that is given Vm sin phi by R. So that is the initial current that we have to use. Whereas in RL circuit we used here 0. But here capacitor. Capacitor means current, some current, as it is short circuit. So that current is this. Thus we have to use here. If we use that here and substituting t equal to 0, at t equal to 0 plus means 0. T equal to 0 here, here. And if we simplify, we will get a value. We will get a value from this equation. And that a value can be substituted here in the final equation here, a value. After substituting and simplifying, this is the final expression. So this is the expression for current in RC circuit. In this is transient response and this is steady state response. This transient response becomes 0 immediately after closing the switch. Within microseconds this becomes 0 and this will be the permanent response. That is the solution. Same thing for RLC circuit, you can check it out. Only simplification, steady state response, transient response is as it is. You will get here simplification. For RL circuit we are getting here this term Z equal to only R square plus omega L square. For RC circuit, R square plus 1 by omega C square. For RLC circuit, R square plus this omega L minus 1 by omega C. So in this form we can reduce the equation. It is clearly given. If we reduce, then in place of this we can write Z like this. You see the impedance triangle also. If you can see, you can easily understand. In RL circuit here R, here only omega L. For RC circuit here 1 by omega C. For RLC circuit, impedance consists of R plus this term omega L minus omega. In that terms we can simplify the equation and we will get the expression. So that is about the RL, RC and RLC circuits excited by AC supply. Only thing is steady state response, there is some difference. That difference is also mathematical simplification, that's all. The thing to be remembered here is while simplifying we have to rearrange the terms like as per the impedance values. So these impedance values, that is impedance, real term or imaginary term X, how they can be represented for RL circuit, RC circuit and RL circuit, that I explained. Okay, that simplification is only the thing you have to understand. Remaining thing is same. The problem also same thing, whether there we are having RLC, here in place of RLC we will be having values, that's all. So that is about the AC transients. I will stop this video now. In the next video, that is only of half an hour of video, we will try to cover the Laplace transform method of solution of this transient response. Here we solve by writing KVL equation or KCL equation in differential form and by determining transient response and steady state response, like that we solve. There something differently we can solve the same differential equation by using Laplace transform. That we will cover in the next video. Okay.